Hello, and welcome to part 2 of the video for lesson 2, and the topic of this portion is going to be viscosity. And we have a viscous pencil. So, if we ask the question, what is a fluid? The answer is it's a substance that deforms continuously under applied shear stress. We're now going to examine the rate of that deformation. Important notation, I use V for velocity and a V with a slash through it to represent a volume. So a subtle notational difference to keep track of two different V's. And what we're going to talk about right now is roughly pages 36 to 38 of the textbook. So let's go ahead and draw our fluid element again. This one's a little awkward, and we'll call that height dy, and we'll start to apply our shear force, tau yx, and there'll be some small differential force and some small differential velocity involved. And as our fluid starts to deform at some different moment in time, there's the new fluid element, and it struck this angle d alpha, and this top thing has translated a short distance dl. So let's examine the geometry implied by this image. We have tau yx is equal to the limit as area goes to 0, where remember on our fluid element we have this area and that force. And it's the limit as the force over the area are small, and that is dF over dA, and that is our definition of shear stress. Now the notation yx means the stress is perpendicular to the y-axis and applied in the x direction. So that's a tensor notation. Well, that's an attempt at a tensor description. Let's examine the rate of deformation. So the rate of deformation is how fast alpha is changing with respect to time. If we examine the limit of that as time gets small, we get d alpha dt, just the fundamental theorem of calculus, and this is the rate of deformation. Now let's look at that rate in terms of the element geometry. Okay, so quick redraw. Alpha dl dy tau yx. Okay, let's look at this distance dl. That's going to be equal to how fast this point is moving, so dv, multiplied by how long that occurs, dt. Because this is just saying this displacement is equal to velocity times time. We also know that dl is pretty close to dy times d alpha. So the dl is going to be roughly the distance struck by that radial segment that's length dy, and for very small angles, that equality is for all practical purposes true. We can rearrange this as the tangent of d alpha is equal to dl over dy. And now we can equate these two things. We have the velocity with respect to y is equal to d alpha with respect to time. That's because these two definitions of dl are the same. So here's where that came from. dv dt equals dy d alpha, dv over dy equals d alpha over dt. Now in the limit, as the dy and d time vanish, we come up with d alpha dt equals dv dy, and this rate d alpha dt is related to the velocity profile. dv dy. That's a very important concept. The velocity profile and the rate of deformation are related. And if that relationship has certain properties, then we can determine whether the fluid is Newtonian or non-Newtonian. And if it's Newtonian, then the constant of proportionality is called the absolute viscosity. So let's transfer these onto another sheet of paper. And we have that the alpha dt is related to dv dy. Now if the alpha dt is proportional to the shear stress, the fluid is called Newtonian. If that's the case, we have tau yx in turn is proportional to the velocity distribution, dv dy, and the constant of proportionality called the absolute viscosity. And we would write tau yx equals mu dv dy. If it's not proportional, let's call that then the fluid is non-Newtonian. And the fluid property is a little bit harder to describe. Now, non-Newtonian fluids exist in real life. Actually, many fluids we encounter on a daily basis are non-Newtonian. There's a type of non-Newtonian called shear thinning. An example of that is latex paint. And those fluids are engineered so that as you increase the shear stress, the viscosity goes down, so it's easier to spread the paint onto the surface you're trying to paint. And then when the shear stress is removed, the fluid becomes thicker until it has time to dry. So that's called shear thinning fluid. There's also shear thickening fluids. I can't think of an example off the top of my head, but both those types of situations can be engineered into fluids. Often, power law models apply, where there's some constant dV dy raised to some power n minus 1 times dV dy. And this group of terms here is called the apparent viscosity. And it's not too hard to look at the structure of this. Apparent viscosity, dV dy on this axis. Here on this axis, so a Newtonian fluid simply says that some constant slope, that's going to be mu over 1. If they're non-Newtonian, and suppose n is like 3, we have stuff going like that. That would be a thickening, and if you have n less than 1, you also have these are both non-Newtonian. And non-Newtonian is probably by far the more common term for engineered fluids, and whether you want to have shear thickening or shear thinning, there are engineering packages that can be added to fluids to make that happen. A common example is motor oil for the automotive engine. Now it would shear thin at high temperatures, but they had additive packages. So 530 oil, for instance, is a viscosity of 5 units, but it behaves at high temperature as if it had viscosity of 30 units, and that helps protect the So let's go ahead and take a look at this velocity profile. Here's a solid surface with some cross-section here. Let's assume that the velocity as we move away from the solid surface, y-axis, is uniform. Along this line, the change in velocity as you change y is 0. But somewhere down gradient, we may have the case where the velocity profile looks something like that. At the solid boundary fluid interface, there's usually a property called a no-slip condition. And as we move somewhere up in the fluid here, away from the boundary, the no-slip is irrelevant. But let's go ahead and examine fluid particle right there. Go ahead and pull it down here, and if we look at that rectangular particle, we notice an interesting thing. The velocity on the top is higher than the velocity on the bottom. And so that implies that the shear is working here, and there's a tau yx going that way, and then that would be how the fluid particle could deform. So we have these shear forces unbalanced. That's what creates the velocity distribution. This no-slip condition has been deduced from many historical experiments, and it's an important assumption that the relative velocity vanishes at the contact point. Now, whether that's really true at a macro level is hard to argue, but certainly at some point in the microscopic world, there has to be a point where fluids don't move very much at the solid fluid contact. This profile is also called a velocity gradient, and the slope of it is related to the shear. These viscous effects are what cause velocity profiles to occur, or alternatively, if velocity profile then viscous, however you want to picture that. And so we can use these simplistic, relatively simplistic concepts to do some practical problems. And we will get on to one of those right now. Here's a personal favorite, but it's a good problem. So we're going to imagine, if you will, a 1 by 1 meter block that slides down an inclined ramp at a speed of 2 centimeters per second. And in the interest of time, I think I'll just go ahead and point through the work that problem. So these are the problem. We have a 1 by 1 meter block that weighs 25 newtons, slides down a 20-degree inclined ramp at a speed of 2 centimeters per second. The block is lubricated by thin oil. Good oil color. So it's going to be magenta oil number 3. There is no such thing as and here's our thin oil. See the word oil right there. And we want to determine how thick the oil must be if the viscosity is 0.5 newton seconds per meter squared. That's kind of a backward way to do the problem, because more importantly, you want to know what viscosity is to produce the proper amount of exercise. So we want to draw a free body diagram of the block and a free body diagram of the inclined plane. So here's our free body diagram of the block. The block here, it has a weight of 25 newtons associated with it. There's a shear force. The oil pushing on the block, if you will. There's a normal force of the inclined plane pushing up through the centroid of the block, and I've chosen the coordinate system where x is in the downslope direction, y is perpendicular to the plane defined, plane defined by the incline ramp, and they differ by 20 degrees about 20 degrees apart. If we look at the free body diagram of the oil is contained in this region between the block and the inclined plane, and so here is my oil agitating that purpose. And we have the property that there's no slip at the oil ramp interface, and there has to be no slip at the block oil interface. So at this location, the relative velocity of the oil relative to the block is 0. Same is true at this location. But because this is sliding down, that point has to have non-zero velocity relative to the inclined plane. That's an important observation. In that case, the block is moving 2 centimeters per second. The oil is stretching at the same rate, 2 centimeters per second at the top, 0 centimeters per second at the bottom, and that creates our viscous condition. Our viscous deformation creates this picture. So now if we write our knowns, unknowns, and governing equations, what do we know about this problem? We know that the block weighs 25 newtons. We know that the angle of incline is 20 degrees apart. We know that the viscosity of the oil is 0.5 newton seconds per meter squared. That's given to us in the problem statement. We know the contact area is 1 meter by 1 meter, 1 meter squared. We know that from the problem statement where it's a 1 by 1 meter block. The unknown is the thickness of the oil and the velocity profile. And the governing equations we're going to apply is F equals ma, and set the acceleration to 0. We have the definition of viscosity, which is Q is equal to mu times dV dy. And we have the definition of shear stress, tau is equal to force over area. Okay, so here's our solution procedure. Let's first analyze the block. We have the sum of the forces in the x downslope direction equal to mass times acceleration in the x. We're told it's at constant velocity, hence the acceleration term must be 0. So the sum of the forces in x is w times the sine of 20 minus the shear force of the oil on the block is 0. Therefore, F tau is equal to W sine 20, which equals tau times the area of the block. Essentially invoking the definition of shear stress, and the shear stress is F over A, so tau times A is now we'll analyze the oil. We'll assume it's Newtonian because we have no reason to believe otherwise. We're not given enough information for non-Newtonian. We have the shear stress is equal to mu dV dy. Multiply both sides by the contact area. Tau A will give us this F. Mu dV dy times the area. So now we're going to substitute in W times the sine of 20 for tau times the area. So we have W sine 20 equals mu dV dy times the area. And we will arrange to isolate the dy term. So we have dy is equal to mu dV times the area divided by W sine 20. And we can substitute in numerical values. 0. I've lost the area. This is a mistake. So it should be 0.5 newton seconds per meter squared, and 0.02 meters per second, 1 meter squared, side power 25 newtons, sine 90 degrees. Up here the degrees, the value of 0.00177 meters, which is about 1.77 millimeters. Would be the coil thickness. And finally, discussion. This problem required us to use engineering mechanics for our statics and dynamics class, find the equilibrium conditions on the block. There is an implicit Newton's third law, which is the force of the block on the oil is equal and opposite to the force of the oil on the block. We applied a no-slip condition to the top and bottom of the film of oil to the same Newtonian. And that would be a direct application of viscosity, of the principle of viscosity. Okay, that concludes the definition of viscosity. We'll do another one live with in a radial geometry to again see how to combine the methods of engineering mechanics from statics and dynamics as well as the fluid dynamics class. So thank you very much for your attention, and we will see you next time.